All right, here we go. Year 12 mathematical methods. It's chapter 1. What you see here, sometimes I put it in, sometimes I don't. I try to keep it consistent and try to update this each year. But it tells you per exercise which dot points you're ticking off from the study design. Okay, so that way you can sort of keep track what you're meant to have learned in each exercise. Most students forget about all these, and you know, by all means, it's fair call. At the end of the day, if you know your stuff, you know your stuff. But it's always nice if you like to be meticulous and consistent. You look at your study design, link it back, and tick it off. Okay, you can link back to which exercise it represents. Yeah. So we've got exercise 1A and 1B. Putting that together. Some of this would have been in your year 11 course, and for some of you who were on my year 11 course last year, I would have taught you the methods 1A already, and 1B too. But I'm going to try to describe it this session, and it is important. Everything that you learn in year 12 methods is about how well you understand the first few exercises, because then that leads you to understanding the harder stuff. Okay, so a lot of students skip the first few exercises. They think, oh yeah, too many language, too many symbols, too many notations. And they try to do the last few topics, for example, composite functions, inverse functions, and modulus functions. Those are the reason why they find that so difficult when it shouldn't be is because their language is poor. So start off with the basics, and that's what I try to do. I try to describe the basics, get your notations correct, then doing the rest is easy. Okay? And the main thing for today, if anything, once you walk out of today's lesson by recess, what I want you to take out is what is a function. Okay, so that's your goal for today. Will you understand what a function is and how do you test it and why do you do that test? Okay, so what a function is. Okay, so let's have a look. Let's have a look at today. We're going to revise some of the notations here. So let's revise. I'm going to try to learn some names as well. I don't have my roll here. Yeah, it's all right. Let's go with this one. What does this symbol represent? Can I please have... Oh, my back just cracked. There's someone who I don't know. No, Ben, I already know you. I want to know some new names. Sorry, what's your name? Is it Harry?
Liam.
Liam, what does that symbol represent?
Null set.
That is the null set. Fantastic. That is the null set. We use that symbol to say that within this group, there is nothing. Null. Okay? Null, empty, or nothing. What does R represent? Can I please have the person sitting next to Liam?
Me?
Yes.
I don't know.
No, what's your name?
Athena.
Athena.
Sorry, I don't know.
Oh, we're not sure. Okay, that's cool. Anyone else who may know what an R is, can I please Momika? Real numbers. What is real numbers though? Okay, so I'm writing here, real numbers. What does real numbers mean, Mazen?
Every number.
Every number, literally. Okay, I wrote it there. Every number that you can think of. Any number that you can think of. 2.17. Pi. Root 3. 8. Negative 1. Negative 1.5. All those are real numbers. 1 plus I. Except for that. Well, 1 is the real part. Okay, so real numbers is every number that you can think of, except when you walk into complex numbers, okay, with the I. So real numbers is every number that you can think of. We use R to denote that. And you'll see that most common when we're talking about our domain and range. Those are notations. Q. Anyone know what Q stands for, Alessia?
Is it integers?
Not integers, that's Z, so that's good. What's Q stand for? Z is integers. Then what's Q? Michael? Not sure? And your name is?
Aaron.
Aaron?
Rational numbers.
Rational numbers. So, what is rational numbers though, Xian? Xian?
Well, multiplication, multiply, and it can have dot points.
It can be fractions. You will think of irrational. Rational numbers can be expressed as a fraction. Okay? It's when you can express it as a fraction and it can be expressed with 2 integers or whole numbers. So for example, number 3. That's a rational number because 3 can be written as a ratio of 3 to 1. Okay? And 3 out of 1, they're both whole numbers. So it can be expressed as a fraction or a ratio of integers. That's what it actually means. Okay? So 3 is a rational number. 4 is a rational number. 1.5 is a rational number because you can write that as 15 out of 10. Okay? Whereas when you write root 3, that's not rational. We say that's irrational. Because root 3, if you type that in your calculator, it's an infinite or no pattern decimal point. Okay, it carries on and carries on. Yeah, so hence why pi is irrational. Root 2 is irrational. Whereas root 4, why is root 4 not irrational? Because it ends up being 2. Okay, so root 4 becomes a 2, and 2 can be expressed as 2 out of 1. So this is irrational. Does that make sense? Yeah, so I'm going to draw a sort of a diagram so you can see. So you got R, which is all the numbers you can think of. Okay, any number that you can think of. Out of all the numbers you can think of, there is a restriction where Q is. Q can only take certain numbers. And those numbers are like 3, 2, I don't know, 1, 1.5, 1.5. Okay? Whereas it can't take root 3, it can't take pi, it can't take root 2. Okay, so those are irrational numbers. And they fit all of this, which is real numbers. Within the irrational numbers, you have now what we call Z, which represents, again, integers, which is what? What is an integer, Basil? It's a whole number, plus or negative. Okay, so it doesn't matter if it's positive or negative. So in the whole number system, I'm just going to rearrange this so we can see it. We have 1.5, we had half, and I'm going to write here 3, negative 4, 5, and 2. Yeah? Then within that, this is now your Z values. So within your rational numbers, so all of this is rational. You can write them all as a fraction. Within it, all the positive or negative whole numbers is Z. So 3, negative 4, 5, and 2 are positive or negative whole numbers, right? But they're also rational numbers as well. And that leads to the last one, N. So integers, positive or negative whole numbers. Then what's, oh damn, I just told it. Hopefully you didn't read it. William, what was that again?
Positive integers.
Yeah, positive integers. Okay, so we call that natural numbers. And if you think about it in terms of your year levels of how you learnt things, when you first came to primary school, first things you counted with your fingers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. These were all natural numbers. Positive, and they were whole numbers. You didn't like fractions, you didn't like decimals, and most students still don't like fractions and decimals. Okay? But that was the time that you learned maths and it made sense to you. You could count them with your fingers, you had lollies, and you're like, I've got 1, I've got 2, yay, you know? But you never really went, I've got 1, I've got 1.5, yay! You know, it's always 1 or 2. That's why whole numbers was easy. Then you went to year 7, high school, and you learnt positive or negative integers. Yeah? That's when negatives was confusing because you only ever gained. You never lost. You're not happy if you lost 2 lollies, you know, you wanted to gain 2 lollies, not lose. So that's why negative was tricky. When you had negative, negative makes positive, that was tricky for you to understand. And then some of you pulled through, some of you didn't, and then you went to year 8 and year 9, which is fractions. And it revises back all the way to grade 3 and 4, 5 and 6, fractions, how to add, how to multiply, how to divide, and you're like, oh my god, I hate this. Okay, and if you put that with algebra, that threw you off as well. Okay, so irrational numbers is where you start in 8, and 9 you learn surds. And how many people hated surds back in year 9, year 10? Irrationals. You're like, what is this? I hate it, I don't know why you have a square root symbol, you don't know how to do it, and all these numbers that comes up, rounding to 2 decimal places, and you keep getting that wrong. That was where it was. And then you finally get to year 11, methods, the first time you saw R. Okay, R was the time when you use, domain X as an element of R, and using null sets as well, so set notations. Technically that was taught back in year 8 as well, but a lot of us would have forgotten it by then. And now in year 12, what are you doing? You're just revising what you've learned. 6th grade, 6th or primary school will let you know. Does that make sense? Okay, so that's one way of remembering it, or think of the diagram, or what have I explained? Or watch the video again, okay? Now, these are the 2 things that most students get wrong, and it comes up in your exams quite often, and those are the things that most students overlook, okay? Because we're used to seeing just R and whatnot. These are the little things to note. So I want you to write this down as your highlight or star next to it. When we do an R, which means every number you can think of, but we put a plus next to it, or on the very top of it, then R plus means it's all numbers that you can think of, but the restriction is it's positive. Okay, so you're thinking about this diagram, it's every number you can think of, just don't include the negatives. Okay? But the one thing that most students forget is this one, the one that I'll put in brackets here. It doesn't include 0. When you do R plus, it never includes 0. And the same thing with R negative, it does not include 0 either. Okay, and the reason why I say this is generally the mistake most students make is in the exam, when you look at the diagram, sometimes they have an open set in their diagram, and you can say R negative, or sometimes they give you R negative, and they don't tell you if I include 0. And most students, when they write the domain, this is what they do. So let's say they said X is an element of R plus, and they were to write their domain. Most students in the graph, so if the graph was an R plus, it will look something like this. Okay, so that's R plus, all real values that are positive, but doesn't include 0. And most students who write their domain without checking, they will say R plus. But that's wrong. Oh, actually, that's right. Okay, but if it actually had this, then that's wrong. Okay, so if you wanted to write R plus, that's fine. But that's including 0. So now you have to learn how to use one of these set notations that you learned to include the 0. Alternatively, you can use interval notation, and you can say include 0 to positive infinity. So you could have done that as well. But if you were to do R plus, you have to use what we call union, which means also include braces 0. Okay? And that's why I'm saying most students will write that R plus, forgetting that that doesn't include the 0. And if you had to include the 0, you needed to. Okay? That comes in. Okay, so you can see what I mean by the topics aren't going to be hard. It's the language that you use, and in year 12, they're very pedantic. Because we don't know if you actually know it. You either did it because you don't know it, or you did it because you did know it and it was a mistake. Okay? We don't know. We always say that you're guilty until proven otherwise. Okay? So we think that you don't know until you show us that you do know. Okay? All right, here we go. So I'm going to just clear this up so I can have a look on this side. So R plus, R negative, please write that down. Highlight the not including 0. It will be very important. Every time you say R plus, R negative, that should be the first thing you think about. Does it include 0? Does it not? Do I need to include it in my notation, or do I not? Okay? Now, one of the ones I just gave you, I gave you union. Now, the first one here, what's that symbol up there? Very top here. What's this one? Intersection, which we learned from probability last year. It means what's in common, where they overlap. Okay, whereas union means it doesn't matter if it's overlapping, it's just saying I want to group them together. Okay, so another way of thinking about it is, in this classroom, if I group this class with my other year 12 class, I should have close to 50 students. That's union, okay? Intersecting is if you happen to be in this class and you happen to be in my year 7 class as well. Okay, so you're not only in my year 7, but you're also in my year 12 class, and hence there's an overlap. You're the one person in both classes, yeah? But we don't count you twice, yeah? So if I included you with my other year 12 class, I don't count you twice, I only count you once, and that's union. Intersection is once overlapping, yeah? All right, so we got intersection. What does that E stand for again? Element. What does element mean in terms of, when we try to describe, what does element mean? Can I please have Ian, what's element mean? Yeah, individuals or a part of. Okay, so when we say X element, so you notice my notation before I wrote X element. This just basically means X is a part of, or is within, or is a group in this group, or whatever it is. The question is, what group am I talking about? The one that I did before was I said X, which is your X-axis values, they are in this group. What's this group? This is your all real values that are positive. Okay, but if I want to specify it with a 0, then I say union, so include 0. Okay, notice I'm using braces, so if I didn't use that, that doesn't make sense. The braces tell you how many individual items you have. Okay, so if I had 0 and 1, I would say, actually 0 and -1, for example. That's what I would say. I'd say, okay, it takes all the numbers you can think of that is positive, as well as 0, -1. Okay? If I wanted to include it as an interval, let's say the graph looked something like this. So I'll do a quick demonstration. Let's say it was something like this. So it's from 0 to positive. This is R plus. That has my 0. Let's say I drew another one from, let's say, closed dot, -5 to -2 open dot. Yeah? Let's say I want to describe that domain. So my graph looks like this. And I want to say X has -5 to -2. And it also has 0 to infinity. Yeah? Now you can use interval notation, or you can use set notation. This is all falling under set notation. Okay? So how would I do that? So I got the R plus. Fantastic. Now, I'm saying union means include. Now, the R plus doesn't include 0. Okay? So I can do two things here. It looks a bit funny when I do it like this, but I'll show you how it is. It's going to be, I'm going to say include 0. And I'm also going to say include, okay, now this is I can do this where I can say I want it from an interval of, what is that again, 5 to -2, open bracket. Okay, so that's, oh, thank you, -5 to -2. So if you read this, it's saying I will take, X will be a part of, or element, means a part of, a group of, within this group here. So what group do I have? I have all real numbers that are positive, which is all this. I will also have it in 0. I will also have it in -5, but including -5. So that square bracket there says you also count the -5 as well. So that's why it's closed circle. All the way up to, so comma means all the way up to -2, but I don't count -2. That's one way of using set notations and interval notation to describe the domain. Does that make sense there? And that's what you would do in exercise 1A. You're learning how to use these notations. I've just done one example. You're not going to get something this bizarre, but at least you understand what each of these notations mean. And this is the expectation you ought to do when you're doing your exams at the end of the year. Okay, you have to use some sort of language, is either set notation or interval notations. Cool. Right. Now, so we've done union, we've got the brackets, braces, we've got close and open, excluding. I'm just gonna, how do I clear this again? Clear ink. Okay, here we go. Now, one last one that I haven't taught, and it used to be a big thing. I don't think well, the examiners at the end of the year, they have this report, and we come to these PDs, and they tell us what to do and what not to do. And one of the years, or a couple of years, they were very pedantic when you're using the symbol exclude. See that backslash there? That exclusion, they were pedantic that you used it correctly in mathematical language. Yeah. If you used the /, they would have penalized you back then. And then there were a couple of years afterwards, they're like, oh, don't worry, kids know what they mean, so we'll just give them the mark as well. So I don't know if that's still true. It could change. And I think for the last 2 years, it's been okay with its / or backslash. And they tell you in the assessor's reports. But I'm just teaching you the correct way right now. Okay, so the correct way should be backslash. And one way to remember it is if you don't backslash it, I will backslash you. I don't know why that says not forward. Did I say backslap somewhere? No, I didn't say it. I must have deleted from my PowerPoint. It usually says backslash or I'll backslap you, but oh well. Okay, so backslash, backslap. Backslash, backslap. Okay, not /. That doesn't make sense. Backslap. Okay? So there we go. So we got X element of, so it means X is a part of all real numbers, any number you can think of, except. So this means except. Okay, so you can write that there. Except for, and then I use braces when I want to talk about one particular number or couple lists, like small individual numbers, and I use braces. If I know it's going to be an interval of numbers, then I'll be using interval notation. Okay? So here I'm saying it can be every number you can think of except for the number 1. Okay, so visually, the graph could look something like this. It could be something like this. It could be all numbers except for 1. Could be a straight line like that. Okay, so it's all numbers. It's just a horizontal line except for the number 1. Okay, or maybe I could have a graph that looks like this. It could be all numbers up to 1, like that. And just that 1 is not included, but everywhere else it's included. Okay, that's what that symbol actually means, or that notation describes. Any questions? Good. Okay. Now, domain and range is your, hopefully we know by now, X represents all your X values, so X-axis values, and range is all your possible Y values. And there's one more thing I need to say. What was it? Implied domain. Funny enough, in my first year, when I first taught the year 11 course, I didn't know what an implied domain is because I knew what it was, I just didn't know it was called the implied domain. It was a new language. And one of my students said, what's an implied domain? I'm like, it's just a domain. Don't worry about it, they're wrong, you know? And then I realized very quickly afterwards what the implied domain is because it was in the year 11 exam, first half, and it came up, and I knew I told the students wrong. So it is a domain. I was correct, but when we say implied, it means they don't tell you. You see, so for every graph, normally, and I'll show you later on, with every year 12 question, they will have a domain, unless they give you a question and they want you to find the domain yourself. An implied domain, implied means obviously they don't tell you, it's subtle, and you gotta sort of, it's implied, right? Root of x, what's the implied domain here? What do we know about root of x that we can't do? What can't we root? What can't we square root? Negative numbers, yeah? So we can't already say that x can take square root of -2 or square root of -4. We know that doesn't work. That's why there's already a restriction without saying so. I didn't have to write a function where I say, you know, this is the proper notation, by the way, which I'll teach you later. F is, I don't have to say that it is r plus r, comma, f of x is equal to root of x. I don't have to use that notation. I don't have to tell you the implied domain or the actual domain, okay? By just writing f of x equals root of x, you're meant to know the only numbers you can take is r plus, and I forgot something. What am I missing?
Smiley face.
No. Oh yeah, you do have a smiley face, yes?
A winning attitude.
I don't know what that means. Yeah, that's what I'm missing. Okay, so that's the implied domain, even though I don't tell you it. Okay, so you're meant to figure that out. And a lot of the questions you're going to do in our SACs and our exams, they're going to have those implied domains and you're meant to know. So the better you can visualize these graphs, the better you can see what the domain is, and the better you use notations correctly, you're getting that 1 or 2 marks. Okay? The worse you are at it, at picturing it, or seeing it, or noticing the domain, you're likely to lose a mark each time. And a mark sounds very little, but if you count it over like 4 or 5 questions, it's a lot of marks out of, let's say, 40. You know, if you're 40 and you lose 10 already from 10 questions, you know, then because exam 1 has 40 marks, 10 questions, roughly, 9 to 10 questions there. If you lost the mark for each one, it's likely you're going to lose more than that. But let's say 10 marks. 10, that's 30 out of 40, which makes it now 75%. You just lost 25% for 1 mark each question. See what I mean? So it adds up. So we don't want to lose marks, not for things that we know, and these little things you can pick up. Okay? All right, let's have a look. So that's exercise 1A. Let's do some examples now. Okay, let's do some examples. Here we go. You're going to have a look at these. You're going to write in your exercise book, see if you can answer these, and I'm going to go through the answers with you. But I want you to have a look at the notations. You've got A equals, and it tells you A is this group. B has this group, so set B, set A. Find A, whatever that symbol means. B, what do these two mean? Sets. And I'm going to answer it with you. I'm more interested in this one here. Interval range and how to write it as on a number line. Use a number line. Let's try that. See what you've learned today. Because I still haven't gotten to what a function is. We're going to first know this, and then I'll go to what a function is. That's the aim. By the time it's 10:25 and you walk out of this lesson, you should know what a function is. See, now you're just learning the language. How are you? Anyone Korea? Anyone Korean? Oh, good. Oh, damn. No, I didn't get to snowboard. We had a couple of things that came up. I was there for 18 days, and it was great. Transportation, much better. It was great. Organised. You can go there blind and you get away with it. You just get around so easily. So transportation was so good. Food-wise, you can get it all over here. Everything just tasted so much the same. Melbourne is not, I find that Melbourne tastes good about many other places taste, except for coffee. Some rice cake. They were so soft and so spicy. Too spicy for me. So if you're a spicy person, that's great. I think what I was probably most shocked by is the culture shock. I think I've been so used to Japan being a very polite country when I go there. I say sorry and they're sorry and they bow and then I bow back to them, they bow back to me and I bow back to them. It's like a cycle until you walk away. So they're really, really polite. So I'm thinking Korea is right next to Japan. It should be the same. And when I go to Korea, I'm telling you, it's just like you get off the train, and even over here, when you get off the train, you should be standing on the sides as a passenger who's about to board, and the people who are getting off the train has the middle, so they walk out. True? Yeah. So I'm standing on the side. So yeah, you go. I'm standing there, and this man comes out, and he decides he needs to go right. So he goes, bang! And he pushed, right into me, and I'm like, oh, sorry. I didn't know how to say sorry in Korean. I should have learned that too. I was like, oh, I'm sorry, and he just bumped, and he just walked off, and I'm like, okay. That's all right, I can deal with that because maybe that's the culture. Maybe, the bubble's okay, everyone's in a rush and they're hasty and they're going off somewhere. And I'm like, okay, I'm all right with that. Until, and this is where it got me annoyed. So it's my turn to get off the train. I'm getting off the train and, I'm looking across. It was my fault too because I was looking away, but I did apologize. So I looked away for a moment because I'm just trying to make sure I'm getting off the right train stop. I looked away and I came in and the guy happened to nudge my shoulder. It was a very light nudge, right? I'm like, oh, sorry. I said sorry and I bowed. I was like, sorry. And he looked at me, he was like, and he gazed at me until I was out of his vision. So I'm walking away, I'm like, sorry. I walk away and I look back and he's like, and I don't understand. I'm like, whoa, that's like a double-edged kind of thing. It's a double standard thing. It's like, you can bump into me and walk off. Whereas if I accidentally nudged you and I said sorry, you give me this grace until I disappear, And
wait, it wasn't the same guy.
No, it was a different guy. And that happened consistently. It was like they were just so hasty. Like for example, Stacey, like my partner, she was going to the gates when you do the My Key tap off, and there's 6 gates. She's just like probably this close, taking out, trying to find a My Key card or their version of My Key called T-Money. And she's trying to take it out. There's like this much space to the gate entrance. And out of all 6 spaces, you have to have one passenger, this old lady, she's just like, and she runs in front of Stacey, and I'm like, but there's 6. And she squishes in, and she's like, Eet! And then she runs away. And she runs through, and in my head I'm like, there's 6 of them! There are 6 of them! You can choose any, but no, you have to go, hey, she's choosing that one. I think that one must be the best one. I'm going to squish in, beep, and I'm going to run off, And so she went in, and she ran off, and I'm just like, why? And it just, over the course of 5 days, I just realized that, there was a pattern, and the pattern is, if you're a senior, so let's say you're married and you have kids, onwards, you have priority. You are entitled to be an asshole. Just walk through, be whatever you want. Just walk through, and then if they're younger than you glare at them, and then you walk away. It was very prominent that with the older generation, they were very, I don't know, you just don't touch them. And if you're sorry, sometimes they had this Korean sort of way of saying it. They were like, and I'm like, whoa, man, I'm sorry. And they walk away, and I'm like, oh my God, what do I do? What do I do? It's so hard to understand it. And so that got me a bit upset just over the trip. Just like, I'm trying to be nice, I'm trying to understand the culture, I'm trying to be like, okay, you're hasty, I'll be hasty too, Like, it's kind of like, I don't know, it just didn't work. So culture was a culture shock. Food was standard. Places to visit, wasn't too bad. I like visiting temples and whatnot. So it was a good trip. But I wouldn't recommend 14 days. I do about 5. Great shopping, about 5 and move on. So that's a tip for you guys. If you ever go to Korea, expect some nudges from the old people. And the great selfie takers. Okay, and they're great at taking photos for you. They're so enthusiastic. I asked so many Koreans of all ages, young and old, and I'm telling you, even the older ones, say, I love this guy. So great. We were at a green tea museum. And we passed, he's like, yeah, I'll take a photo, and he takes it. And I'm telling you, he's doing his limbo. He's like, and then he actually comes over here, and he's like, and he was so enthusiastic about taking a photo. And I was like, no, this is fine, this is good. And he's just like limboing, he's just like checking, all right, that looks good. And I'm telling you, it did look good. It was really good. It was like, and every one of them is very good. It doesn't matter how old they are, they're just enthusiastic about a photo. For you, I was in a cave and I had a grandpa tell me what to do. It's just like, no. And I'm like, okay. And it's like, I'm like, okay, I'm moving aside. And he took a great photo. It's amazing. Yeah. So, if you need some great photos, go to Koreans. They're really good at it. I don't know, it's like there's a 101 class on how to take a photo. They're just there. It's really good. Impressive. But yeah, that's my trip for Korea. Isn't the best. So, but then, having said that, I don't like the heat over here. I like the cold. Cold's always been good. So it's too hot down here for me. It was sub-0 degrees down there, -8, -4, -10 at times. And it's so good. 2 jackets on and you're fine. You just walk around, you know. All right, here we go. I'm going to go through the answers here. So A, intersection means what do they both have in common? A has 1, 2, 3. They both have a 3. So and a 7. So therefore, I would write with braces, 3, 7. Use the braces. Whoops. Next one, A union me means put them together, but remember, you don't double count. Yeah, it's kind of like grouping our class with another year 12 class. You don't double count yourselves. Okay, we just count the number of students here and we count the number of students over there. So they're individual. So when you write them out, it should be 1, 2, 3. There's overlapping 3 there. There's no 4, there's no 5, there's no 6, and there's an overlapping 7. Okay? There you go. So A union B equals that in the set of A intersection B, which is 3 and 7. Yeah? Next one. For A is this, B is that. So it says, I want A and exclude B. Okay? So A exclude B means whatever you have that is B, get that out. Okay? So currently B has 3, 4, 5, 6, 7, and there's a 3 and a 7 there. That is in B. I don't want 3 and 7. So my answer should be 1 and 2. Whereas the second one, B, tells you I want in whatever B is, exclude. See, that backslash means exclude whatever A is. In A, I have 1, 2, 3, and 7. And in B, I again have only 3 and 7. That's the same as A. So my answer here would then be B exclude A would have to be 4, 5, and 6. Hands up if you got all 5 correct so far, 4 correct so far. Fantastic. Good. Next one, illustrate each of the following intervals full of real numbers. And I wrote they use a number line. Okay, so I wanted you to read the brackets here. They both mean including. So if you did a number line, you can say -2 here, do 0, and then do 3. All I wanted to see was you using closed circles all the way up to closed 3. Okay. If you do the same for B, so B, you're doing a number line, you can say -3, 0, do 4 here, and you don't include -3, and it goes all the way up to include 4. If you're doing C, how do you show negative infinity? You use an arrow, so I will start at 5, so at 5, this is 0 here, 5, I'm including 5, but I'm going all the way to infinity, so I use an arrow. Okay. D, they're both excluding, so you should have -2, 0, 4, open circle from -2 to -4. I mean to 4. Okay, so it doesn't include -2 and doesn't include 4. Yep.
We have to draw a number line in a test. Do we have to draw the line and the line and the line? Or can you just draw the top thing and then apply the number?
No, you have to use the line. The reason why they teach you number line first, you actually learned this in year 7. The reason why they use that is because this is the first step for you to describe the domain of the x-axis. Okay, so that's why it always has that number line there. It's actually describing the x-axis values, and you're learning to describe the domain. These are potential domains when you answer your questions. That's why they're getting you to train sort of that way. That's why you do need that axis. Okay. Yes, Martin?
Let's see, why is it colored in
Because 5 has that closed bracket. And closed bracket means that you include 5. So like this one, that's include -2, include 3, so I use closed circles. Whereas open bracket means you don't include. That's why I had an open circle. And -3 is an open circle. And so the open brackets means don't include it. And the way we show it is with a closed dot. Yeah? Excellent, good. There we go. That's one potential mistake gone. So that's good, because we use those dots when we're doing our graphs in our SACs and our exams. That's very important to know whether you include it or not. Okay, yep.
You have to do 0.
No, I'm just using the 0 so that you can sort of see the -3, 4. Yeah. Because most of the time when you're actually answering these type of questions in an application question, there's an axis already. So you just follow that. I'm just doing that as a number line. It looks nicer. That's all. -3, 0, 4. Negative side, positive side, 0. Yeah, it doesn't really matter. Okay, and E will then have to be -3 to infinity. You don't ever include infinity, by the way. So meaning that you can never have something like this. That never exists. Okay, we just don't know what infinity is. It's a concept. It's not a number, so we don't know what it is. Therefore, it is always open circle. I mean open brackets. Okay, but to answer the last one, we've got, let's say 0, -3, not including -3, all the way to the positive. Easy, hands up if you got all of that correct. Excellent, fantastic, good. Finally, we're going to use all of this knowledge. Now I'm going to give you a couple of graphs, and I want you then to tell me the domain. So remember, all of this was a skill for you to learn how to use the notation, how to read the notation. That number line there is so that you can read the domain. Now, if you can read the domain, you can read the range as well. Okay, so I'm going to give you a couple of graphs, and I want you to find the domain and range. I'll do the first one, and you do the rest. Okay, so here we go. Let's try this one. The previous page was you had to sketch the graph. And these have the graph. Okay. Eventually, you have to know how to sketch the graphs. For now, you're going to use your calculators to sketch the graph. But here we go. Let's have a look at this one. I'm going to do the first one here. It says state the domain and range of the relations. And I'll talk about what a relation is afterwards. Okay. Because remember, at the end of this session, you want to walk out knowing what a relation is and what a function is. Well, if you know what a function is, you know what a relation is. Okay. So here we go. I'm going to go with this first one. This is technically a function. Okay. We've got a quadratic function, and I want to talk about its domain and range. Now, if you just ignore the y-axis and just look at the horizontal axis along the graph, you can see that the line can go on infinitely onwards. So that means your horizontal axis can go on and on. You always have a coordinate for your x-axis. So my domain, in this case here, so what I'm trying to say is this can carry on, and I always will have an x value. So what I mean by that? So that's why if it keeps going on, technically my x-axis can always expand. So therefore my domain, which I'll write x, can take all the values of every number. Okay, because if I want x to be 1, so when x is 1, when x equals 1, I have a coordinate. This is 1 something. Okay, I don't know. But I know x coordinates, it has a 1. If I want a 2, 2 has a coordinate on the graph. It's 2 something. I don't know what that other coordinate is. I don't know what the y is. But I do know that it has an x coordinate of 2. If I want to know the coordinates of, I don't know, let's say 5 here, I'm looking at the graph, and yes, it does have a coordinate. It has 5 something. So that's why I know my domain can be every single number, because 0 has a coordinate, -1 has a coordinate, -2 has a coordinate. If you keep drawing this graph onwards, technically every negative number will have a coordinate on the graph. And every positive number has a coordinate on the graph as well. Does that make sense? Okay, so I'm just referring it to the x-axis. And I'm just looking at the x-axis. Okay, the x-axis there, 5, has a coordinate on the graph. Whatever this number is, has a coordinate on the graph. It's all about the graph. Okay, don't get confused by the x-axis and the y-axis. We're just saying, does it have a point on the graph? It does have a point on the graph. It is part of it. Okay, so the domain is anywhere on the x-axis if it has a point on the graph. In my case, it has everything. Whereas your range, on the other hand, see range, which we use y, the y coordinates, you can, I'll rub off this part too, so you don't get confused, and I'm going to use a different color. Let's use blue. We use blue. You can see that y, the y values of 1, when y equals 1, you have 2 coordinates. But it doesn't matter, you've got a point on the graph. So that exists. So y is 1. Y has a 1, so the range has number 1. It has number 2. See, 2 has a coordinate on the graph. It has 0, so at 0, it also has a coordinate on the graph. At -1, it also has a coordinate on the graph. At -2, it has a coordinate on the graph. Where doesn't it have a coordinate on the graph? So below -2, if I said, does this graph have a -3 for the y values? It doesn't. So if I actually looked at the y values, and I continued it on, if I just wrote -3, and I followed on, see, I'm not touching. horizontally, I'm not touching the graph at all. That's why -3 can't be a part of y, or y cannot be a part of -3. It can't have a -3. It can have -2, can have -1, can have 0, can have 1, can have 2, can have 3, can have 4, and you just keep drawing this up. It goes on infinitely. Which is why when you write out your range in terms of set notations, it can have -2, can have -1, can have 0, 1, 2. Now you don't want to write that because it goes on forever. You can have -2.5. I mean, no, -1.5. Yeah? So the only way to write that is you'd say, well, it includes -2 and it goes all the way to positive infinity. Okay? Notice when I write the numbers, and this happens in my year 12s for the SACs as well, lowest number on the left, largest number on the right. Don't switch those two. Okay? It's just a poor notation. And though I understand what you're saying, you're doing it wrong. Okay? Smallest number on the left, largest number on the right. And that happens with this kind of notation as well. You know how use in equations, so you might do x is something like that. Sometimes you guys do it like this. Which is true. You know, it's true, but we always conventionally write the small numbers on the left and the larger numbers on the right. Okay, so the first one is the preferred answer. Don't do that. Okay, yeah.
Is it preferable to write as opposed to like negative infinity, just infinity, like in the
instead of writing like plus?
Yeah, well, yeah.
Oh, you can write the plus. It's only when it's negative that I make sure I put a negative on it. Positive, I don't. It's sort of like 3. You don't write +3. You just write 3.
And like the X domain for the domain, is it like preferred to write just the R symbol as opposed to writing like bracket?
Oh, I get what you mean. Yeah, so set notations versus what you're calling an interval notation. There's no preference. Okay. Yeah. You can use R or you can use interval notation as long as you get it correct. Doesn't matter. Most of the time, obviously, I don't want to find the most efficient way. So if I knew, you know, instead of writing that answer, instead of writing it as negative infinity to infinity, technically that means all real values. It just takes longer to write, and I'll just do R. But by all means, you could have done it like that too. You could have done X element of that, and no one would penalize you on that. It's absolutely fine. Okay. How do we feel with that? Domain and range. Pretty easy? Yeah? So I want you to do B, C, D, E, and F. And I'm going to give you 6 minutes because 1, 2, 3, 4, 5. So just a bit over a minute each to do the domain and range. And I'm just going to rub this off so you don't get confused. Oh, there we go. Cool. Okay. Should have a go with that. And then finally, once this is all done, that's all exercise 1A, by the way. So set notations, interval notations, number line, and domain and range is all in 1A. And 1B is one that we're getting to functions and relations. And you won't understand that until you know how to use these language. Okay. And that will conclude for today.
So do we need to do 1A? Like exercise 1A?
I generally prefer you don't. I want you to jump to 1B because that's the nitty-gritty stuff. But if your notations suck and everything like that, do it. So it's more about your own discretion. When I give you the questions, it's really for you to figure out what are you weak at, what you're good at. If you can't do it, do it. If you can do it, move on. You know, learn. Be smart about your learning. You know, you don't have to do everything I tell you, but you have to be ready by end of year. So do whatever you need to, but just be ready for the SACs, for the exams. Then I'm not angry. I'm angry when you don't put in effort, you complain about it. So if you don't put in the effort, you don't do your homework, and you come to me and it's like, I want a 40, sir. I'm like, okay, well, have you studied? It's like, no. I don't know, I get annoyed, I get invested in you. I'm like, I'm working hard for you, and what are you doing? And like, I'm playing games, I'm watching TV, I'm going out, I'm sleeping. You know, then I get annoyed, I'm like, why can't I do that? Why can't I sleep? Why can't I not play games when I could? You know, instead I worry about you guys. So I prefer that if I'm putting the effort, I like it to be reciprocated. All right, let's have a go. 6 minutes. And then I have 25 minutes to teach you functions and relations. And just make sure to log on to Schoology. Missing 3 lessons next week. You're missing 3 lessons with me. Did I see what?
My cover. Yeah, no, you haven't. Yeah, that was me. Yeah, I know. But you don't lead out. You don't make someone's majority. You did. You don't. I have the chat logs. I have the chat logs. You can't pull that shit out. I may just apologize for my best.
So I don't know who's in E. It'll be good. Close to 50 students. You know, it's like 3 English classes so far. Mrs. Bassler has 2 classes. I have 2 classes. And Mr. Morales has like 50, 60 something. We each hold about a third, actually a quarter because it's 14. Almost a third. So we have the power. Oh yeah. Alright, time's up. Let's have a look. B. What was your answer? Can I please have Aaron for B? What's my domain?
Negative infinity to 2. Oh, close bracket on 2.
Say it again.
Negative infinity to 2. Close bracket on 2.
What am I missing?
Open bracket on the infinity.
Good. Fantastic.
Oh, right, yeah, my bad.
Excellent. So x is an element of open bracket negative infinity to 2. So always the smaller numbers on the left, larger numbers on the right. Okay, so notice that my x values, yes, I can have the 2. Okay, but I can't have anything after the 2. There's no dot point or coordinate on the graph. So it is anything on the negative infinity all the way up to 2. Okay, so that's my domain. What's my range?
R.
Good, fantastic. See, R would be, that's correct. Okay, next one, C. Can I please have, who have I chosen? Let's go, was it Shirley? Good, open bracket negative 2 all the way to 3, open bracket, notice it doesn't include, okay, and it's going from negative 2 all the way to 3, and you don't include that. That's my domain. What's my range? Fantastic. So include 0 all the way to 9, open bracket. Okay, so be careful there. Most students look at the coordinates and they think it's 4 to 9, and it's not. Your range is how far do you have it on the graph. And on the graph, I go as far as 0. So my y values go from 0, including. So I'm including, I have a 0 on the graph, all the way up until the highest y value is a 9, but it doesn't include 9. That's why it's close brackets 0, open brackets 9. Okay, so be careful with those notations there. Yeah? Next one, D. What'd you get for D, William?
So the domain
Yep.
is open bracket negative 3 to 1, which also has an open bracket.
Fantastic.
The domain is open bracket negative 6 to 2, which also has an open bracket.
Fantastic. Good. Okay, so you're looking, in this case it's pretty easy. you're looking at your horizontal values. It goes from -3, that's your x value, to 1, but they're both open circles, so you don't include. And then your y value is -6, which is the smallest y value, to the largest y value, which is 2, but they both don't include those open circles. I mean open brackets. Okay. Next one, E. What'd you get? Let's go with Jun. -4 to 0. What's this one for? Domain or range?
Domain.
Domain. Good. So we got x is an element of. Say it again. What am I missing? Good, fantastic. Close brackets on both sides because they both included. Notice that this is a circle, so that means the radius is 2 units, and that means another 2 to the left as well. So from -2 to the 2 left makes it -4. And it's up to 0. That's my domain. What is my range then, Jun?
0 to 4.
Good, excellent. So it's going from 0 to +4. Fantastic. F. What did you get for F? Sorry, what's your name?
Verity.
Verity.
X is R.
Is R?
Yeah. And Y is open bracket X and then 2 bracket.
Fantastic. Good. We have an asymptote, so it means we're approaching as close to 2, but you never get to 2. You never actually have a coordinate on 2, so that means 2 is never included. So therefore you don't have a closed bracket, you have an open bracket, and obviously it goes all the way to -infinity for your y values. X values, obviously you can keep going, therefore it's real values. Yep.
Are there other ways you could write that, like real numbers less than 2, or like anything like that?
Oh. I think you can. I'm just trying to think of what it looks like. So it would be y's element of r and then less than 2. That seems to make sense. I just haven't seen it that way. I don't know if I should encourage you to write it that way, because I feel like they can be nitpicky about it, and I don't know what they think, but argumentatively, if you had time to debate with them, yeah,
Okay.
should be right. It's fine. No, because the domain is your x values, true? So all the positive x values are on this side. But not only that, they also have, this side here has all the negative values as well. See, like if I drew -1, so if x was -1, it has a coordinate on the graph. So if you said that x is an element of r positive, you're not including that point. So r plus would only be from here. That's r plus, because this is all the x values, 1, 2, 3, 4. That's where you have all the positive x values, so that's on the x-axis. But note that the graph also extends this way, so you have all the negative x values as well. Does that make sense?
Yeah.
Right. Excellent. Good question. All right, how do we feel about that? Excellent. Fantastic. Well, we are now moving on to finally and some of these answers are wrong, by the way, so ignore that. Just look at my videos instead. I'll adjust this. I'll fix it. We're finally up to what I wanted you to learn, and I've got 25 minutes to get you to understand this. Okay? So, this is what I want you to copy. Make sure, and for some of you, I've taught in year 11 already. I would have taught what a function is. It's a good revision again, but it is important so that you understand every other function. So you don't take the word function for granted, because we learned quadratic functions, we learned linear functions, we learned exponential functions, logarithmic functions, sine functions, cosine functions. A lot of times you don't even realize that you're using the word functions, but it's given a restraint and you haven't realized what it was, okay? Because a function is a specific type of a relation. That's what I want to talk about today, okay? So here we go. First thing is, what is a relation? Okay, so in the previous question, they talked about a relation. So if some of those graphs that I showed you before were a relation, then what is a function? What constitutes as a function? So a relation is simply a set or group of coordinates. So an example would be something like this. If I just did this coordinate, this coordinate, this coordinate, this coordinate, and I connected the dots this way, that's called a relation. If with the same coordinates, if let's say I decided to connect it this way, that's a relation. If I decided to do this, that's a relation, okay? If I decided to draw a graph that was like That's a relation, okay? Because all it just means is it's a relation which is a set or groups of coordinates. Okay, so you have a group of coordinates and every dot that I drew in that line there is a set of coordinates. Okay, so when you put it together, it is a relation. So when you have all possible graphs that you can think of, then within it, when it has a certain property, we call that a function. And that one property, there's only one thing you have to understand, which was what they try to assess you at the end of year when it comes to a function. Okay, a function only has a unique y coordinate. Okay, so think about it in a function or in a coordinate system where you have x and a y coordinate. It doesn't matter what graph you draw as long as you end up with one y coordinate for every x coordinate. You can have multiple x coordinates, but as long as you only have one y coordinate to it. So an example is this. So if I draw, and just keep in mind of that machine there. So for example, a linear graph. That's the first thing you learned back in year 9. That's a linear function. Why is that called a function? It's because when you think about, let's say 1, x is 1, and this is the coordinate, you have 1, 2. For every one coordinate, there's only one y value. There's only one, so the 2 is only paired with number 1. Think of it as like a monogamous relationship, okay? So in this case here, for every number 1, you only have number 2. Okay, so 2 is very, I was going to say 2 is very faithful, but it's actually x values are very faithful. Okay, it's 2, they could be a bit polygamous. All right, so for example, so that's a linear graph, and that's a function. So it only has one y value. You can see if I drew 2 over here, that will have a point here. This could be 3, so this could be 2, 3. So you can see that the x values are very faithful to the y values, is 3. Okay, so there's only one y. So there's only one y value, one y value. So when will you have 2 y values? I'll show you an example. Let's change it to a surd function, okay? Square root function. Technically, square roots have a positive and a negative graph. So when you actually type root has a plus and a minus. This is what a square root function should look like. A square root relation should look like. But when it's a square root function, this is what you learned last year. That's why it's called a function, because for every x value, there's only one unique y value. That's why it's called a function last year. Okay? Why is it a relation? Because this is the true form. This is what the relation is. This is a group of coordinates. But why is this not a function if I can continue the negative part of it? Is because for one x value, I have 2 y values. See what I mean? So for 1x, I can have the coordinate 1, negative 2, but I can also have 1 and 2. Okay, so in this case here, 1 is polygamous. I mean, x is polygamous and y is polygamous. Monogamous. Okay, I'm getting confused by the 2. Okay, so what you can see is x is not unique anymore, but that doesn't matter. Okay, because that's not what we want. We just want a function has y values that are unique. Okay. Now in this case here, this is not unique. You've got this repeated x values. So when you put in the number 1. This is the problem. So the way I like to draw it is this machine. If I put the number 1 in, so this is my x, I can potentially have negative 2 or 2. Because those are my 2 coordinates. If I put in 1, I can either get a negative 2 or I can get a 2. That's a problem, because that doesn't fit my definition of what a function is. A function says you can only have one y value. Okay? Meaning that I always want x to be monogamous, y to be polygamous. When you have that switched around, if x is polygamous and y is monogamous, that's wrong. Okay, so 2 is paired with 1, so it's faithful with 1, but then negative 2 is also faithful with 1. So y values are faithful. That's wrong. Okay, that's not a function. Whereas x here, this is not faithful. So 1 has negative 2 and 1 has 2. That's when we don't call that a function, we call that a relation. Okay, so the relationship between 1 negative 2 and 1 and 2. Yeah? But if we switch that around, how do I have a function where I put in 2x values and I get 1 y value? Okay, I'll show you an example of that. An example where you can have 1y, is it what? 2x values for 1y. So let's draw a quadratic graph. Why we call that a quadratic function. You see, in this case here, if I chose 2, let's say negative 2, okay, what you can see here is when x is 2, y is 2. When x is negative 2, y is 2. So what does this mean? This means that if I put the x values into the machine, it comes out only one answer. One unique y value. So if I put in a negative 2 now, so you see if I chucked in a negative 2, then technically I only have 2. If I chucked in x equals to 2, I also only have 2. So this is what we want. This is what a function is. A function describes when you have y values as polygamous, and x values are, monogamous. Okay, so it's for negative 2, it's only paired with 2. Negative 2 is not paired with anything else. It's not paired with any other y value. X is always faithful, y is not. Okay, so x is always faithful, x is always faithful, but y has 2 partners. Does that make sense? Yeah? So we're just saying, as long as you get only one unique y value, you put any x values in, and you get one y value, that's what a function is. That's as simple as it is. If you walk out of this lesson, that's what I want you to understand. Because now you can look at all types of graphs that you know, and you can figure out why is a cosine a function? Why is a straight line a function? Why is exponential a function? Why is logarithmic a function? I'm going to draw it all up for you so you can see the theory that I'm talking about here. So let's have a look at from year 9 all the way to now, all the graphs that we've learned. Okay, so we learned straight line. It was clear that x was faithful to only one y value. That's true. For one x, there was only one y. Then we moved on to quadratics towards the end of year 9 and year 10. What we can see is x is still faithful to one coordinate, and x is still faithful to this coordinate here, but this coordinate, y coordinate, is not faithful. That's a function. Okay, because you can have this being monogamous and that being polygamous. Okay, so you can see I put in 2x values, I only get one y value. Okay, so that's a function. Then we lead on to, let's say, cubic. Why is that a function as well? See, a function, if I drew it like this, why is that a function? Let's have a test. Let's have a look. So if I chose any x values, it's got this coordinate here, so this is one y value, but notice this y value is paired with 3 x values. Okay, so all these x's, so I can have x equals negative 2, x equals negative 1, and x equals 5. What I'm saying is in this machine, when I chuck in x equals negative 2, x equals negative 1, x equals 5, they're all paired to this y value. See, y is polygamous, x is monogamous. You can have all these x's, you only have one y. Okay, this is called a function. That's why cubic was a function. See, when you choose x, there are multiple multiple x values for the one y. I haven't used any other y values. I've got x here, x there, x there. Okay, this is called a function. When I put it into the machine and it spits out only one y value, all the x's, if it comes to one y value, then you know that's a function. Okay. How do we feel about that? Does that make a lot of sense? Yeah. Okay. If we now move on to what other functions we learnt, rectangular hyperbolas. Same thing. You see, if I chose an x value here, it's faithfully paired with only one y value. Okay, there's only one y value. That's why it's a function. If you think about a sine function, same thing as well. Even though it goes up and down infinitely, it's still, for every x value, there's only one y value that they're faithful to. Whereas y is polygamous with many x's. Okay? That's what a function is. Okay, so technically, if it's not a function, if it doesn't fit into this description as a function, we call it a relation. Okay, another way of thinking about it as well, if you were given coordinates rather than a graph, what you're looking for a function, okay, for a function to exist, you'll be looking for repeated of what coordinate? Repeated of what coordinate makes it a function? Say it again. y. That's all you're looking for because it's only one y value for many x's. So if you're writing out the coordinates, as long as you've got a repetition of your y values, it's a function. Okay, so for example, this one right here, group A, wouldn't be a function. Okay, because if I put in the coordinates here, I've got 1 for when x is 1, I've got -2, and then 1, I've also got a 3. So that's a relation. Okay, so x is polygamous and y is faithful to it. Okay, so that's wrong. Yeah, it's always x is going to be monogamous and y is polygamous. That's when it's a function. Yes?
So it doesn't matter how many times it reoccurs, so long as the y stays the same, it's a function as well.
Yeah. As long as y only has only one y. There's only one y, one unique y value. Whereas all the x's, you can repeat the x's, doesn't matter. So if you think of it as the machine, doesn't matter how many x's, you can put 1,000 into this machine. There's only one. So what that implies is this y person has 1,000 x's. Okay, so it has 1,000 x's. That's why that's a function. Okay, it's a functional relationship. Yeah. Any questions there? We're good. All right, fantastic. So now let's go into some pedantic things. So that's what a function is. If you walk out of this lesson, at least you know what a function is. The only thing you now have to look at, don't worry about these. You can look at that during your own time. First part of the question will ask you to determine whether it's a function or a relation. You can either, if it helps, you can start off by plotting the coordinates and you visualize the graph and then say, oh, is it or is it not? Alternatively, if you understood what I was trying to describe, then you know that all you have to look for is repeated y values. Because if you have repeated y values, it means it's unique for every one of them. Okay, but when you have repeated x values, repeated x values, then that's wrong. Okay, that means for one x, you have 2 different y values. So repeated x's. So let's have a look at this. This has -1, -1. That's repeated x's there. That is not a function. And I can show that diagrammatically. You see, I can say, all right, at -1, I now have y equals 1. So that's one coordinate there, and at 2 as well. So 2. See, that is not a function. Okay, when you have 2 repeated y values, so y is now not polygamous. Y is very faithful to x. And this y is also very faithful to x. This is not faithful. Yeah, it's always y is the one that's cheating. Okay, x is meant to be faithful. Okay, that's how it works. Right? So that's why that's called a relation. And what I've just done there as well, I've also sort of implicitly ingrained in your head what we call the vertical line test. Okay, so what I've done is if you draw a line down on the x value, if you find another y value to it, it is a relation. We do a vertical line test to test if it's a relation or a function. Okay? And that's why I'm saying you don't have to memorize these, you don't have to write it as your notes, because it makes sense if you understand what a function is. If you understand what the term or definition of a function, you don't have to memorize these tests. It just makes sense. As long as you get one y value for every x value, you're good. It's not one x value for many y's. Okay, that's not what you want, right? Okay, so the first one is obviously a relation. What about the second one, B? Is that a relation or a function? Function, fantastic. -2, -1, 0, 1, 2. No repeated x values. Function. Next one. -1, -1, -2, 2, and 4. Relation, repeated x values again. You can draw that and you can see that x is not being faithful. Next one, D. Is that a function or a relation? Function, good. -1, 0, 1, 2, 3. X is very faithful and you could have a polygamous relationship, 4, 4, 4, 4, 4. So 4 is paired up with 4 x's. Okay? That's a function. Technically, if you draw that graph out, it makes sense it's a function because -1, 0, 1, 2, 3, if they're all paired at 4, see, these are the coordinates. You can see that's just a straight line. And that's what you learnt back in year 9. Linear functions. Okay, that's why that's called a function. Okay, because it only has one y value, which if it repeats, it's a function. Okay? All right, how do we feel about that? Is that pretty good? Yeah? Excellent, good. I've got now about 5 minutes left just to go back to, don't worry about this. This is just me describing what a function is in case you didn't understand it. It was just machines and whatnot. I will go back to this one actually and talk about how to write a function notation, which I'll do in the next lesson. But we go vertical line test, which is the one we just did. How do you test each one of these quickly to see if you have a function or relation? Notice, vertical line test, like I said, if this x value is paired with another y value, you can test it with a vertical line test. You see, if I chose 1 here, when x is 1, you can see you got 2 coordinates. That's a relation. X is unfaithful. We need x to be faithful, yeah? This is faithful because every x value is only paired to one y. Okay, so x is faithful, hence function. Not faithful. Relation. Okay? Faithful. Faithful. Unfaithful. A relation. Faithful. Function. Easy? Okay? Now, as your last part for today's session in the last 5 minutes, within your functions, I want you to copy this down as well. So we understand what a function is. We've now broken it up into 2 types of functions. And the first 2 that you learned in year 9 and year 10 are 2 types of functions. See, this one, x is faithful with y and y is faithful with x. So we call it 1x to 1y. So it's 1, 1, 1 to 1 function. If we look at the next function, this is quadratic. If I chose an x value, so let's say, a y value at 1, negative 1, sorry, you can see that it has 2 x values to 1 y value, meaning x is faithful, so 1x, sorry, not 1x, many x's to 1 y. That's all we want. We just want, these are called functions. So this is the type of relations you can have. You got a one-to-one function, so x is faithful, y is faithful. X is faithful because it's connected to only one person, but y is not faithful. There's only one y. So if you're looking for one y to many x's, y is not faithful. Okay, so one y, this is a function. So you got one-to-one, many to one. This is a many to one, many x's to the one y value. When you say one to many, that means one x to many y's. Yes, Trent?
What does many to many look like?
This one.
Oh.
Because for every x, x has 2 y's, but y also has 2 x's. Okay, so that's why both x and y are polygamous. Right, so that's a many to many. So many x's to many y's. Yeah? So this is a many to many. And then this is an example of 1x. So there's only 1x to many y values. You see that's a 1 to many means, you see for 1x value, I've got 2 separate y values. Okay, 2 different y values connect to the 1x. Okay, that's why it's 1x to many y's, so 1 to many. This is called a 1 to many relation, because it's not a function. See, vertical line test, it's saying that x is not monogamous but polygamous. So this is a relation, that's a function. Function, relation. Yeah? Many to 1, so many x's to the 1 y value. 1x to 1 y, 1x to many y's, many x to many y's. Is that easy? Okay, so it's always x to y, x to y, x to y, x to y. And that concludes your session for 1B. Easy? Fantastic. Thank you. Thank you. Nailed it. Okay. So the only one thing I need to teach you is function notation, but we'll do that next session. I'm sure you got a lot of work already. So 1A, 1B. I will post this video onto YouTube and link it to Schoology as well, so you can watch it again, in case you've forgotten any of the things I said. But otherwise, you guys can pack up and wait for the bell to recess. Welcome back to 2018. Year 12. Sorry?